So in Java, okay, since I am discussing Java, basically I am discussing the bytecode. Same applies to the Kotlin as well. Okay. Now in Java, memory can be divided into two parts. Okay, one is your primitive and another is your object. Okay. So primitives are the basic fundamental data types that language provides. Okay. For example, your int, your float, your character. Okay. All these are basically your primitive types. Okay. And object types are basically the complex data types which are built on using the primitives. Now, there are different way Java handles primitives and object. For example, I will give you an example. Suppose I have a box object. There is a box class which has got three properties, okay? Width, height, and your length. Okay? This is your int, this is your int type, this is your int type. Okay? And this is your box object. When you create your box object using the class, you need to create this box. Okay. Suppose in the constructor it defines them, or suppose we have written our own constructor, for example, that we are passing for width, height and length the values 2, 3, 5, for example. Okay. So the objects are stored in heap. So now we can define memory in two terms. There are two types of memory. One is stack and another is heap. Okay. We'll understand both of them through this example. So when you create a new object, this is stored in the heap memory. Okay. And this returns a reference. This returns what? A memory address. Where this is the memory address which identifies the location in the heap where this object is created. Okay. So this memory address is stored in the box. Okay. So this box is a reference variable. The size when you will see in the memory, this is the size of an int basically. This stores the memory address. It can be, for example, 64-bit on 64-bit system and 32-bit in 32-bit system. Okay. So it depends on the implementation of OS also. So when you create a new object in the heap, it returns the memory address which identifies the object in the heap and assigns to the variable. Okay. Suppose this was enough method. Okay. Suppose this was in a method. So this will be stored in the stack and this was actually in the heap. I'll give you a detailed picture of this in the example. So now you understand that when you create the object, your heap memory is utilized to store all these ints, and a reference and some more space is used to identify this box and some other properties of the box. So this returns the memory reference of the heap storage, and that you store in your stack. Okay. Now if you can calculate, it will be 3 times size of an int plus some extra information. For let's say it's take the information as a size of int. So when you create a box, you're actually taking 4 into a size of an int of your heap memory. Okay. So you need to understand that where your object is going, which memory is being utilized, so that you can, there are various things associated with heap that we'll understand. Okay. So Now you understood how the object is created and stored in the heap and what actually this box is. Okay. Now I'll give you a model to understand what's happening in this case. Suppose this is the RAM of your device. Okay. And this is the heap space allocated to your application. Okay. So now when you create a box using the new keyword, okay, when you create an object, this allocated space is for you in the RAM. You don't have the entire RAM for you. The system, Android system, only gives this much of memory to you for use. Okay. And suppose you created box 1, so box 1 will get stored, take this much of memory in your RAM. Okay. Suppose you create another box 2, it will be given this much memory. Okay. Suppose you create many boxes. Okay. Box 3, 4, 5, 6, 7. Okay. Now when you try to create, for example, box 8, this memory is not sufficient to store your box set. Okay. Then what will happen? Okay. How will you be able to create your box? There will be two scenarios, either out of memory error, system will throw and your application will crash, or GC will run. Okay. So we will understand both of these scenarios. Let's suppose all the boxes are free for garbage collection. What do I mean by free? We'll understand later. For now, let's suppose that if I remove box, I am able to delete this box 1. Okay. So when this condition arises that I need more memory space to store the object that we are creating, what system will do? It will run a GC. So it will try to remove all the objects that are not required. For example, 5, 6, 7 was not required. So it will clear the space, it will remove that from the memory, and it will also rearrange the objects, called compaction. So now with compaction and removing the objects which are not required in the application, it creates the space so that you can store your new box. Okay. So this is the way your heap, this is your heap, this is the management of your heap. Garbage collection is a management of your heap space so that your application can recreate the object it requires. Okay. Now there is one interesting thing here, is that when you run your application, okay, suppose this is your RAM. When you run your application, system will not provide you this size of the heap. It will first give you some small amount of heap. Okay. And then as your requirement of memory increases, it will provide you more space. Okay. Till it reaches a limit. Limit is the large heap. Okay. So till it reaches a limit, that is the large heap, your application will grow in your heap size. Okay. So your application grows in the memory provided by the system till a limit. Okay. So now you may be wondering that why not, and there is a condition that you can ask for the system for this large heap. You can ask the system that, look, I need the space, entire space that you can allocate me, provide me initially. So you can start your even application with the large heap, but it is highly discouraged to do that. Okay, there are two reasons for that. First reason is that system does not allow every application to ask for the large heap. Large heap can only be asked by those applications which are resource intensive. For example, photo editing apps, their classifications of the app that OS takes understand that it can provide them large heap. So that includes photo editing apps. Okay, second is that even if you get the large heap, it is not advisable to do that, because suppose you have a large area to manage by the GC. Okay, so whenever GC will run, it will try to scan through all the heap area, okay, and will compact them and then free all those resources. So your GC will take longer time. Okay, so there is an interesting property of GC that garbage collection has two basic methods, in which two basic scenarios in which it runs. Okay, garbage collection can be called a small GC and large GC. Okay, so you have two scenarios in which a GC runs. Okay, one is your large GC and one is your small GC. It will be around 2 milliseconds. Okay, and it will be around 50 to 100 milliseconds. So a small GC runs in a different thread and your application can smoothly run. The role of this small GC is to clear out the dead object. So if small GC is running, there is no problem for your application. But if large GC runs, this is also called stop the world GC. So it will stop your application. Your application will halt and it will then do the compaction and the memory reference clearing, so that it will take around 50 to 100 milliseconds. So when this happens, your UI, suppose if it has, its frame rate will drop. So user will experience a lag in the application because your application has been stopped and your frame rate has been dropped. Okay, so we don't want the large GC to run very frequently, but if you have a large space because you asked for large heap, then for this area the large GC will take longer time, so your UI will more flicker. Okay, so you need to be very careful that you don't want to run this large GC very frequently. So if we create the large number of objects, okay, large number of objects we are creating, and larger the objects, more difficult, more GC call will be there. So we don't want to increase the number of objects we are creating, because then GC will have to run, large GC has to run. If size of the object is very large, then also large GC will run. So we need to minimize both of the things in our application to make it fluid. Okay, yeah, so if suppose the object size is larger, okay, suppose this is your heap space, object size is larger, object 1, you want to create object 2, for example you want to fit this into this space. Okay, so now it cannot be fit because size is much larger, so it will have to run the large GC. Okay, so when the size of the object is greater and you are creating that, then the probability of GC call will increase. Second, if suppose you have a number of objects, okay, you creating large number of objects, if you want to create another object, there is a probability that this will be filled, so large GC will again run. Okay, so till now we understood that how our object creation goes into your RAM and how GC comes into a play and what types of GC runs in your application. Okay, now we will have an understanding that what happens if multiple applications are running in your Android device and then you are creating your application. So what scenario does that lead to? Because your application can also be a part that is running either in the foreground or in the background. Okay, so suppose this is your RAM. So there were some applications which were running from before. Okay, this was your app 1, app 2, app 3. Okay, now your application is in the foreground and it started with a small amount of heap space. Okay, these apps are in background. Now as your application requirement grows, your size will increase. Okay, suppose it increase in a fashion that it requires more space. So OS will manage this for you, that suppose you require more space, it can clear some other app to free that extra memory you need. Okay, so this app will be killed and on destroy will be called for that app by the system. Okay, so whenever your app is in the background, so now you understand in what situation it can be killed. Okay, so your system will kill other application to provide your application the required memory. Okay, now if you suppose fill up all the space that is allocated by you, then obviously system will throw the memory out of error. Okay, out of memory error. Okay, okay, so this was the overview of how your application is using the RAM, and when your application runs alongside other application, how the system is managing the RAM for you. Okay, now we will see, we have talked much about heap. Now we will talk about stack. Okay, so basically stack is associated with a thread. Okay, so whenever one thread is running in your application, it will have a stack memory specified to that thread by the system. Okay, it depends on the system what is the size of the stack. So each thread will have a space allocated which is called the stack memory for your thread. Okay, now whenever a method is called which is called by this thread, so whatever you do in that method utilizes the stack. Okay, so there is an interesting property of stack that first it can only store the primitive types, and second it can only store the references. Stack can only hold this type of memory. Okay, so now suppose one thread was running. Okay, suppose this thread is some background thread you have created. Okay, this thread is allocated with a stack memory. Okay, now this calls up method 1. Okay, so you have suppose, okay, let's move that downside. Okay, so that you get a more better picture of a stack. Okay, suppose now thread is here, maybe background thread or whatever thread it is. Okay, and this calls the method 1. Okay, this calls your method 2, this calls your method 3. Okay, method 1 internally calls method 2, and then method 2 calls method 3. Okay, so one thread will execute the code in method 1, and then it will execute the code in method 2 and then method 3. Then method 3 will return to method 1, and then this will result, and finally your thread will return with some result from this method. Okay, now as this thread enters into this method, this creates some variables. Okay, it takes some memory which goes into the stack. Similarly method 2 will take some stack memory, and this will create one node above this node, okay, and then method 3 will create one node. When this return, this will be cleared, and similarly this will be cleared, and after it finally returns, your stack will be cleared. If any time suppose the stack get filled, that this method 3 for example requires some space in the stack, but stack is full, then you will get the stack overflow error, okay. And this is the way how stack memory is associated with the thread, and how the stack get filled and released, the process for that, okay. So this is basically a very fast compared to your heap, and because this only have the GC role is not there, okay. So whenever thread returns, your stack automatically clears up. So this is an automatic management, you can say. But before that, I will give you one more thing into picture, okay. So this was one thread calling methods, okay. Now I would want you to remember this, because I will ask you a question based on this, okay. Suppose this is an object, for example your box that you created, okay. So this box can be accessed by any thread at the same time, okay. Each thread has its own stack. So whenever suppose two threads are entering into a method, it will have two sets of stack, so the memory allocation will be different, okay. So it does not, there is no conflict between those threads, okay. But now your object is in heap, multiple threads are trying to access that object, and they have the capacity to do that. So this is a critical problem of your Java programming, okay, that multiple threads can access your object in the heap. So this you need to synchronize it. You will have another lecture on multi-threading, we will understand how to do that, okay. So basically in some conditions we want that an object should only be accessed by one thread at a time. So you need to synchronize the access of the object, because otherwise this will lead to multiple problems. For example, suppose you have a database of, for example, a transaction, a bank transaction, okay. There are two transactions that want to happen, okay. One is crediting the amount and one is debiting the account. So till one action has not been finished, you cannot do the other action, otherwise your data will become encrypted, okay. So that's why synchronization is important, and synchronization is important for managing the heap instances, okay. Now giving this picture of your stack and heap, I'll take an example to define that where actually instances are getting stored. So now suppose you have a function or a method, okay, public void do something, okay. This gets, for example, int a and box b, okay. Now here we are doing certain things, for example int I equals 1. Why am I doing that? Just for example, now we have integer I1, for example, this is I2, this is for example 5, okay. Now I'm going to create another box C, which is new box, provide the length, width, height, okay. Now I'm going to create another variable which takes, for example, C, okay. Now what I'm going to do, I'm going to make B equals C, okay. Now this method must be called by a thread, Either your main thread will call it or background thread you will call it. Some thread will call this method. You are passing int a and box b. In Java, when you call a function, a method, okay, so function we call in Kotlin and method we call in Java. These are just jargons. So when you call this method with int a, for example, so this will be passed by value, and object type, primitive types are always passed by value, and the object types are passed by reference. Okay, you must remember this. When you are calling do something with integer a, so when you call this do something, for example somewhere you call this do something, okay, suppose this was int a is equals to, for example, or let's I equals 10, and we pass this 10, you have box dummy, for example, new box 238, for example, pass this dummy. Okay, you have called this method, okay, and this method runs this block of code. When you pass 10, so your int I was allocated here, okay, in some other function, okay, some other function it was created. Okay, now when you pass 10 here, so this a will be created in the stack of this thread, and this will be a different node that we found out. For example, this was something do work method, okay, do work called do something with these values. Do work will create one node, okay, and do something will get another node. So this int I was in the do work body, so it will be in this node, okay, and your box, when it will be created, this box will be created in the heap, and a reference will be returned, okay, and this reference will be stored in the stack. So not only the primitives are stored, but also the reference of the objects are also stored in the stack, and that references can belong to both primitive and your object. Okay, now this 10 is here, this box dummy is in the stack, okay, in this node. This was your do work, and this is your do something. Okay, now when do something is called, this 10 is copied here, so your a will be having a copy of this. Okay, when you change a, this 10 will, this I will not change. So that it means by saying pass by value, that is it is copied into a different variable in the stack of the caller, the calling. Okay, so this will be 10. Okay, when you modify a, this will not get modified. Box B is passed by reference, meaning that your heap space is there. There is a reference dummy. So a new reference B will be created in the stack. Okay, and this will again refer to the same object. So if you change the box property using the reference, your actual object which was created in do work would also change. So this is mean by passing by reference, pass by value, pass by reference. Okay, so now when you call do something, it will create two variables, two storage in your stack for do something. One is for the int I10 and the reference of box B. Okay, now here you are creating I1. So can you answer to me which part of memory this will take? So this will take the stack. When you call integer I2 equals to I5, now tell me, what's the answer? Where it will be stored? So 50% are saying stack and 50% are saying heap. So I'll say that you both are correct. How? when you create an integer, okay, so this is a class. This 5 is actually in Java called auto boxing. So basically what it is doing, it is actually creating a new instance of integer and passing it 5. When you can write 5, but this is actually what happens. So this is called auto boxing, okay. So this statement is actually creating a new object. A new object always go in the heap. So this will be stored in the heap, and this will be a reference to that object in the heap. So it takes actually both memory, stack and heap, okay. Now this is very clear from the above example only. C will be a reference which will be in the stack, and this will be in the heap. Now tell me again where this D will be. Exactly, very good. So it will be in stack, okay. This is just a reference, so this will be in the stack. And C was also a reference, so basically C is a reference which is referring to another reference, okay. So indirectly it is referencing to the heap. Now this is an interesting question. If I change B, if I write B equals C, assign C to B, okay, C was your new box with different property. Now B was passed. I assign B as C. So will this dummy will change or not? So basically you are changing the reference. This was a different reference variable which was pointing to this box in the heap. Now when you have used that reference to point to a new object, so this will now refer to a new box, and that will not be referenced by the B now, okay. So when you are writing a method, so these things are happening for your stack and heap, okay. If I write a equals 20 here in this method, what will happen? This will change, I will change or not? Yeah. So this a was actually a reference to the stack. A new variable was created in the do something node of the stack, okay. So now when you assign a as 20, so a new 20 will be created, and this will now refer to that 20, okay. Okay, so till here we have understood about how actually the stack and heap are getting used. Now let me ask you a question. The question is, okay, so listen it carefully. Suppose there are two threads, okay, you call this method using your main thread, and you call this method using some background thread, okay. So two threads are called. Suppose your main thread was running come till here, okay, and your background thread come till here, okay. So background thread has reached till box C, okay, and your main thread is at integer I1. So in the stack memory, okay, how many int I is there? For the, this is for your main thread, this is your background thread. How many int I variable memory space is in the stack? There will be two stacks for background and main. So int I will be 1 in both of these stacks, okay. So very nice. Now we'll take memory leak. So memory leak is very important for Android because you have limited memory, as you saw, and if something is leaked, first is what is the meaning of a leak, you need to understand, okay. then only you can appreciate the management of your code to reduce the memory leak. So suppose you have your RAM and this is your application. Okay. Suppose there is object 1. If GC is not able to clear object 1, okay, then it is called a leak. Okay, because this much space is now virtually not available to your application. Okay, so memory leak is basically GC's inability to reclaim it. Okay, so giving you a better definition, suppose you have two components. Okay, suppose this is a parent component and this is a child component. Okay, parent has created child. Now suppose child, this is the expectancy in your application about this lifetime that this child will be required in your application. Suppose your application created this parent component, which is required for, let's say, certain operation. Parent created a child which is required for certain operation. When the operation where child component was required is finished, okay, and still child component is not able to garbage collect, when this can happen, suppose this parent stores the reference of child. Parent is storing the reference of child. Okay, child component operation is finished, but since parent component is storing the reference, this will not be garbage collected. So child component will reside in the memory till the parent component lives. So this is actually your memory leak, when some component exists beyond the expectancy of the desired expectancy for that component. Okay, so how this reference is actually affecting the garbage collection, we will understand. So this was the overview about memory leak, what we are calling as a memory leak. Okay, so in order to understand how GC actually works for memory management, when your application runs, first thing that will be created, your instance of your application. Okay, this object will be created. This object in turn creates other components. For example, in our case, network service, database service. Okay, and as activity 1 is launched, so activity 1 is launched, then this is created. Okay, now when activity this further creates other objects. Okay, and this further creates other objects. Okay, so this tree like structure is formed where the parent reference creating the other object and parent is holding the reference. Okay. We can also share the components. So each child is referenced by the parent. So when GC starts, it starts with the application. Okay, GC will go down the tree to find out all those part of this tree which are not being referenced from anywhere. Okay, suppose this activity 1 was launched and now activity 1 launches another activity, and when activity 1 launches another activity, is ask the system to launch it. It does not create the instance, it asks the system to launch another activity. So system, what it does, it creates the another activity and set this reference to null for activity 1. So now when GC comes, and this activity for example has created many other instances. Okay, so when GC comes and it sees that this activity 1 is being referenced by this application, so it will be for given network service and database service is also being referenced by this application, it will be cleared. But this activity 1 is not being referenced because the reference is set to null. So GC will collect all the instances which are associated with the activity. Okay. So now this memory will become free from your heap space. Okay. Not only from here, suppose for example, this not only happens from the top position. Suppose activity 1 launches a fragment. Okay. Suppose activity 1 launches a fragment. Okay. Fragment 1 is removed from the backstack. So this will be set, reference will be removed from the activity. So when GC comes, it will garbage collect the fragment. So whenever from the chain your reference is cleared, that branch becomes available for your garbage collection. Okay. So this is how your GC works. But now let's assume that you have some broadcast listener. Okay. From your local broadcast listener. Okay. Activity subscribes to this listener. So your local broadcast listener will hold the instance of this activity, and local broadcast is maintained at the application level. So even if you ask the system to launch, for example, another activity, activity 2, this reference is removed from your application by system. But will it be garbage collected? What do you think? Okay. What do you think? Will activity 1 will be garbage collected or not? Yeah, exactly. So it will not be, because now local broadcast is holding the reference of activity and this instance is being held by the application. So this chain is being referenced by the application. So this is actually called a memory leak. Okay, so this is very important to pay attention about memory leak. So what we do in this case, that in on create we attach the listener to the local broadcast, and for example on start we do it, and on stop we remove the reference from the local broadcast. Okay, so that's why it is important to pay attention to memory leak. Okay, to understand what component hierarchy is there in your application. Okay. So this was an overview of how a GC runs. Okay, what do I mean by garbage collection, and why garbage collection is, why understanding the GC and the way garbage collection works is important for our application. Okay, so I hope everybody understood. Yes, one more thing that I will add is that in Java, whenever you are creating an inner class A, okay, you have an inner class B. So inner class implicitly references the class A. So suppose you have an activity, and activity created an inner class for your async task. Okay. So suppose activity on destroy was called, but this async task was running. Async task is an inner class, it will implicitly reference to the activity. So till your async task is running, your activity will not be garbage collected. Okay, so this is also a memory leak. So when you create static inner class, then this implicit reference is not there. Okay, so in order to, suppose for example you are creating a static inner class, then you cannot refer to this activity, you need to pass this activity to the inner class, and whenever you are doing this you can store it in a weak reference variable. Okay, we'll talk about weak reference in the lecture when we talk about the synchronization. Okay, so yes, this was the complete picture for today's lecture.